All right, so section 11.2 is properties of power series. And so let's overview just a little bit um, what the objectives are, things like that. So we defined what a power series was last time. And so basically you can kind of think of it as a function that's defined in terms of a convergent infinite series that has a certain kind of form to it. So we're going to sum, say k goes from 0 to infinity, ck x minus a to the kth power, okay? So the definition of our function has an infinite series component to it, which basically means when you plug an x in, wherever the series converges, that makes that x an element of the domain of f, okay? And so what we're going to do is look at some of the basic properties here. So what do their domains look like? Okay. One of the early things that you saw when you looked at new classes of functions was what does the domain of that function look like for different examples? Okay. And then other things that we can ask is how do we, what kind of calculus can we do, right? Because we've learned about derivatives and integrals and so forth. What does that mean for these kinds of functions? All right. And these are just kind of some of the basic properties. We'll look at more how are then they applied after that. Okay. So just to start off with an example, and this relates to domains and things like that. Here's a function g, and it's defined in terms of this infinite series. So let's think about this just for a second. What we have here is actually a graph of what the function g looks like. I don't know what g is in terms of like trigonometry or logarithms or exponentials or polynomials or rational functions. It might not be any of those things, basically, okay? Instead, it has the series form to it. Now, as a power series, what we could think of is that this series is expanded about zero, okay? So when I'm looking at a series like this, we would say that this is expanded about a. So that x minus a piece here, okay? So the first thing I can look at this and say there is no a, so it's like x minus 0. It's expanded about x equals 0. Well, that's right here on the x-axis, okay? What you see about the graph is that it's well, first of all, this actually is an even function. Notice that all these powers would end up being even when you plug k's in, and this is an even function. That gives a little bit of rationale for generalizing what we mean by an even function. The power series end up only having even terms. An odd function would only have odd terms. We'll see one of those too. Um, what else can we say? Well, just notice that there's some nice symmetry about the center point with how far the domain goes out. So we end up seeing that our domains of power series functions end up being nice and symmetric about the center. Okay. Um, and so just to kind of go over this a little bit, again, this is a definition of what a power series looks like. It's a function whose rule form looks like that. Okay. Again, the CKs are the coefficients, A is the center, and the basically this interval of convergence is what we can think of as the domain. It's all the x values where the series converges, okay, where the rule makes sense. And what we're going to be interested in is how do I find the domain, and then like how do I do calculus on these things? What can I do with it? And there's basically three cases for the domain, okay? Basically, you can have the case that where it converges everywhere. And we'll see that in some important examples. Like for example, when we start doing Taylor series, which is like starting with a function f and coming up with its power series, the interval convergence for like our trig functions, sine and cosine, will be all real numbers. Same for e to the x and a lot of other things. So this is one possibility. Another possibility is that you end up with a domain picture that looks like this. Basically, it's centered at A, and it goes out here to A plus R and A minus R for some radius of convergence R, okay? Now, it might be the case that it converges on the edges here, but usually what matters the most is having this nice connected open interval of absolute convergence in the middle, okay? The third case is the hard case, is the case where the only place where the series converges is at A itself. Okay. And the reason that that would always work is when you plug in A, you just get 0 to the kth power. So like basically for any kind of power series like this one, f of A would just be C0. Okay. Um, does that make sense? Anytime you plug in A, all of those higher order powers would be 0 terms in the sum. And so, yeah, the only thing that would be non-zero possibly would be the first term. So it's those three cases. How do you find, so basically, how do you figure out which one you're in? One, two, or three? Well, it all has to do with running a series test like we saw before, okay? And so typically what you end up doing is using the ratio test or the root test to find the interval of convergence, all right? Especially the open interval of convergence. That's the most important piece, okay? So let's do some examples where we can kind of see that happening. So we've got three examples here, and they're actually going to follow all three different cases here. The first one I actually recognize because it's a simple power series function. It's going to end up being the function e to the x, okay? And we'll see why it's e to the x in the next section, I think, okay? But how do I deal with something like this? Well, basically, what we want to know, here's the idea, is because I see this factorial here, I'm going to try the following thing. The question is where, or when I say where, how about for which x does this converge? That really becomes the question. For which x does this converge? Okay. Well, okay. So what you kind of want to do is remember when we were looking at a sum like this, and we wanted to apply the ratio test, all right? What you're going to do is look at the k plus first term divided by the kth term and take the limit as k goes to infinity. So we're going to go limit k goes to infinity, absolute value of the k plus first term divided by the kth term, x to the k divided by k factorial. Okay? So that becomes the limit as k goes to infinity of what? Well, let's see. I'm going to rewrite this. X to the k plus 1 from the top there divided by x to the k times k factorial. Sorry. So when I do times the reciprocal here, you'd have a k factorial on top, k plus 1 factorial on the bottom. So I'm going to rewrite that as k plus 1 times k factorial. Get some cancellation. All right, so if we're good there, what we end up looking at here now is the limit as k goes to infinity of absolute value of x times 1 over k plus 1. Now that might look a little funky because I'm trying to take a limit here. There's an x involved and a k involved. Here's what you have to think to yourself. Think in your mind, think x is fixed. Okay, that's what you have to be thinking to yourself when you're looking at that limit right there. Okay, x is fixed. It's k that's the thing that's moving. Okay, when k moves, it forces this term right there to 0, and I'm thinking about x as a constant. Okay, so the result of taking this limit is absolute value of x times 0, which is 0. Okay, so we've just computed the kind of the row value, the limit of the k plus first divided by the kth term in the ratio test. Okay. Now, since we got 0 and 0 is always less than 1, basically rho is less than 1 for all x. That implies the sum converges absolutely for all x. So minus infinity to infinity is our interval of convergence. Okay. So let's do another one where we have to do a little bit of work. We'll do a couple more where we have to do a little bit more work than that. So looking at B here. So I'm going to rewrite what that was real fast. So k goes from 0 to infinity, minus 1 to the k, x minus 2 to the k, divided by 4 to the k. All right. So this time, because everything is a power of k, I mean, technically I could use the ratio test again on this and it would work just fine, or we could use the root test, okay? So to use the root test, what we're going to end up doing is we're going to compute the limit as k goes to infinity of the kth root of the absolute value of the kth term, okay? So minus 1 to the k, x minus 2 to the k, divided by 4 to the k. Right? Now, you can easily do a kth root of all of those different things. What I would first do actually is evaluate the absolute value. So that negative 1 to the k term just becomes 1, all right? And this is going to look like the limit as k goes to infinity. Kth root of a kth power, they'll undo each other. I'm going to get absolute value of x minus 2. There's absolute value bars here, okay? Divided by 4. All right? So what does this tend towards as k goes to infinity? Well, it tends towards this value, right? Remember, k is fixed. Or sorry, x is fixed. K is the thing that's moving, all right? So again, I have to think to myself, look, x is fixed, right? So k is the thing that's moving here. There's no k, so I'm just taking the limit of a constant, right? So x minus 2 over 4. All right. Now, what I have to think to myself is the root test conclusion, right? The root test conclusion says that when you take the limit as k goes to infinity, the kth root, absolute value of the kth term, wherever that is less than 1, right? Wherever this is less than 1, you get absolute convergence. Greater than 1, you get divergence, okay? So whenever x minus 2, absolute value over 4 is less than 1, you get absolute convergence. Convergence. When it's greater than 1, you'd get divergence, right? So what that's going to correspond to is if I multiply both sides by 4 here, you get absolute x minus 2 less than 4, okay? And now, so what I just did is I solved for this absolute value. Now what this allows us to do is now think of this as a picture. Basically, when the distance from x to 2 is less than 4, you get convergence, right? So here's a picture of what that looks like. If 2 is right here in the middle, right? If I go 2 plus 4, I'm over here at, I guess, 6, right? If I go 2 minus 4, I'm over here at negative 2. If you're anywhere inside of this nice interval, you get absolute convergence, right? So my radius of convergence is 4. It's that number right over here on the right-hand side, okay? And there's my open interval of absolute convergence. Now, one other little piece about this that we can point out is what happens when we're at one of the boundaries, okay? So what happens on a boundary here? Can we say, do we get convergence or not, all right? Now, that's less important than this interval, this open interval of absolute convergence. But because some of the textbook problems might say, hey, interval of convergence, think about what happens on the boundaries independently, okay? So let me show you what I mean by that. So if I plug in x equals 6, that was right on the edge, right? And so this becomes the sum. K goes from 0 to infinity, minus 1 to the k. 6 minus 2 is 4 to the k, divided by 4 to the k. Well, that's the sum. K goes from 0 to infinity of minus 1 to the k, which diverges. That diverges by the divergence test. It just oscillates between negative 1 and positive 1. The terms do. The terms don't go to 0, okay? What about the other boundary, x equals negative 2? Well, if I plug negative 2 up into that series, now you're summing up. K goes from 0 to infinity. I've got negative 1 to the k. I've got negative 4 now to the k divided by 4 to the k. And now you're just ending up summing k goes from 0 to infinity. You're just adding 1 to itself over and over again. That clearly diverges as well. But see how when you have a nice finite interval of convergence, if you want to talk about what happens in the boundaries, you have to take those two special cases. Sometimes the sum exists on one or the other, sometimes it exists at both, and that would give the full interval of convergence. Okay. Well, let's look at part C. Another one, but just to show that last example of a series that really just doesn't converge anywhere except for 0, okay? So this is k factorial, and then I got x to the k. All right. Now clearly this converges when x is equal to 0, by the way, because this would just be 0, right? You're just adding 0 together every time. But if we tried the same thing and I looked at the ratio test, okay? If I try to compute the limit as k goes to infinity, absolute value of the k plus first term, that becomes absolute value of k plus 1 factorial times x to the k plus 1 divided by absolute value of the kth term, something like this. Now, what ends up happening here is when we get our cancellation, this is k plus 1 times k factorial, so those guys cancel. A bunch of the x's cancel. This is k plus 1 times x, okay? So once again, this is equal to, well, this is definitely equal to infinity when x is non-zero, right? Infinity or minus infinity, I should say plus or minus, depending on the sign of x, okay? But it's equal to 0 in the case where x is equal to 0, okay? So what that tells us here is that this row, it's only 0 when x is 0, less than 1 when x is 0. Otherwise, row is greater than 1 or doesn't exist, okay? So basically, by the ratio test, the series converges only for 0, x equals 0. Everywhere else it diverges. That diverges. All right. So we're going to do just one more of these, I think. And then we'll look at a couple of other things that we can do with power series to get us started. So here's another one with maybe a little bit more interesting interval of convergence action happening. I'm not sure. But let's start off with this. We got so this time we have the following thing. You've got this is now centered at 2. Notice, okay? This is centered at a equals 2. We'll just note that. So we expect our interval of convergence to be around a equals 2, all right? Nice and symmetric. Now I can, again, just go ahead and use the ratio test, which is my preferred method to do these problems. Even on that one where we used the root test, the ratio test would have worked. It's the stronger option most of the time for these problems, okay? So I'm going to compute the limit as k goes to infinity, k plus first term on top. Okay, and then the kth term on the bottom. So x minus 2 to the k over root k. All in absolute values. Big, huge tower. Top times the reciprocal of the bottom, we're going to get a bunch of cancellation. This becomes the limit as k goes to infinity. You're going to have the square root of k over k plus 1. Again, top times the reciprocal of the bottom. That's what a k ended up on top. And then times what? Well, a lot of factors cancel here, top to bottom. So you have the absolute value of x minus 2 just to the first power. Okay. Now again, x is fixed. X is fixed. So this whole factor right here is just a constant. The only thing that's moving is k. Since this ratio is nice and balanced, inside the square root, the limit is 1. And so we end up with 1 times x minus 2. And that's our row value that we get when we compute the ratio, the limit of the ratio, okay? Remember, this thing converges when rho is less than 1 in size. It converges absolutely, okay? So basically, this converges absolutely for absolute value x minus 2 less than 1. That means our radius of convergence is equal to 1. Whereas before, in the previous examples, we had the first part. In part A, it was infinite. In part B, I think it was 4. And in part C, the radius was 0, just a single point. So our radius of convergence is 1. And so basically, a picture would look something like this so far. I know that 2 here, I only go 1 to the right and 1 to the left, adding and subtracting 1. I get absolute convergence in that entire black region right there, okay? Now let's look at what happens on the boundaries this time because something a little bit more interesting happens. So it's worth seeing a case like that. So what happens on the edges? So if I was to plug in, for example, x equals 1, okay? So boundary, try x equals 1. Well, this becomes now the sum, k goes from 1 to infinity, of negative 1 to the k divided by root k. Okay, so what does that look like? Well, this is an alternating series because of this minus 1 to the k. The terms are decreasing and go to 0, right? So my claim is that this converges by alternating series test. Okay, all right, it's alternating. The term size is 1 over the square root of k. It decreases. And the limit as k goes to infinity of 1 over root k is equal to 0. Okay, so basically what I've got to do is update a little bit here. Instead of having a parenthesis here, I want to put a bracket because I know that that should be part of my interval of convergence. Okay, now if I try 3, because let's try the other boundary case. What happens when boundary is 3? X equals 3. Again, I'm plugging in to our original series here. That becomes 3 minus 2 is 1 on top. Now I've got a sum. K goes from 1 to infinity of, now this is 1 to the k divided by the square root of k. Let me rewrite that. That's the sum. K goes from 1 to infinity of 1 over k to the 1 half. This is a divergent p-series. P equals 1 half series. So it converged on one end and it diverged on the other this particular time. So that means that ultimately our interval of convergence was 1 to 3, right? But our radius of convergence was still equal to 1, but this is our interval of convergence overall, okay? Now we're really mostly interested in that open interval of absolute convergence on the inside, but I'm just, again, trying to show that one little piece about handling the boundary of the interval of convergence carefully. Second. Okay, so next up we're going to look at some properties of the power series that we have. Like there's a couple of main questions, like what can I do with a function that's defined this way? Number one, like what kind of operations can I do? What kind of calculus can I do? Another question would be, what does it converge to? That second question is really, really hard and just generally not an easy thing to be able to answer. Um, and oftentimes it wouldn't have an answer that was satisfactory anyways. But what we can do is at least understand a few properties. And so first thing is like some algebra of power series. So when you have power series functions that converge on the same interval, okay, they converge to different functions on the same interval. Whether or not we can write these in terms of other transcendental functions or not is neither here nor there. But it turns out that if you add those two series together by combining like terms, you get a new function that converges on the same interval. Same for multiplication, and same for composition with uh, uh, with a continuous function, basically. Um, all right, so let's see here. So we're going to use this as an example to help us understand a connection between starting with a function and writing down a power series. Okay. Now in the next section, we'll talk about Taylor series. We talked about Taylor's theorem and Taylor polynomials in the first section. And that really generally talks about how you take a function and write down what a series would look like. But here's what we can do. We can use some of these properties that we're looking at right here to try to come up with series expansions for these functions based on a fact that we already know. So one thing that we already know is how geometric series converge, okay? Now, what we saw previously was that the sum AR to the k goes from 0 to infinity. This converges to A over 1 minus R when the absolute value of R is less than 1, and it diverges otherwise, okay? So all we're writing here, it's the same thing, just that the A we've written as 1, okay? And we replaced the letter R with the letter X. Other than that, everything's exactly the same, okay? So for part A, here's what I want to point out. Look, I can think about this x to the fifth times 1 over 1 minus x. And now I can simply replace 1 over 1 minus x with this series, okay? So this is x to the fifth times the series, x to the kth power, right? And now what I can do is actually just multiply these two things together, all right? And so I can rewrite this as the sum, k goes from 0 to infinity of x to the k plus 5, right? And this becomes, the power series for this particular function, right? Now, where does it converge? Well, because this converged on the interval from -1 to 1, and this converges everywhere. Well, what they have in common is the convergence from -1 to 1, okay? So basically, think of it this way. This factor converged minus infinity to infinity, and this factor converged -1 to 1. So it's going to be the intersection, whatever those are, which is just the smaller piece, okay? So my interval of convergence there ends up being -1 to 1. All right, so let's do a couple more of these because they're pretty short to do. So for part B, what am I thinking here? Well, basically I have a 2x instead of an x here. So it's just a little bit of a substitution you can think to yourself, all right? So basically if I let, how about this? If I let kind of u equal 2x, then I have 1 over 1 minus u, right? So think of it this way. You don't actually have to write this substitution in here. I'm just writing u for a second. This becomes 1 over 1 minus u, which then has to be the sum k goes from 0 to infinity of u to the kth power, right? Well, what that means then, of course, is that 1 over 1 minus 2x is going to be equal to the sum k goes from 0 to infinity 2x to the kth power, okay? Which we could leave it like this, or we could separate it out a little bit. Right, that is 2 to the k times x to the k. Right, so there's my series expansion for the function that we started with, okay? Now, where does this thing converge? Okay, now you could do what we were previously doing, but then you'd be doing too much work. So in other words, you could use, for example, the ratio test on this and find the interval of convergence. But the easier thing to do is use this fact we know about geometric series. Because I just used geometric series, think of it this way. This piece here converges when -1 is less than u is less than 1, right? That's right here. So that means our series converges where -1 is less than 2x is less than 1, just replacing u with 2x, okay? Now solve for x. So -1/2 less than x less than 1/2, just dividing by that positive number 2. So our interval of convergence is -1/2 to 1/2 for this series, okay? One more. So here we've got 1 over 1 plus x squared, okay? Again, I can think of this as, if I wanted to think of that as 1 over 1 minus u, what would u have to be? Well, u would have to be minus x squared in order for that to work, okay? So that kind of needs to be the substitution piece. It's the same idea as before, though. So this is then going to be the sum, k goes from 0 to infinity, of u to the kth power. In other words, minus x squared to the kth, right? Which is going to turn into the sum, k goes from 0 to infinity of -1 to the k times x to the 2k, right? So I just put the kth power on the two factors, the -1 factor right there, and then the x squared factor. All right, so there's my power series expansion, okay? And again, if I want to start thinking about interval of convergence, the original, like the 1 minus u piece, that converged where -1 was less than u is less than 1, okay? So for us, that means where -1 is less than -x squared is less than 1, right? And so, so where does that happen? Well, this happens when 1 is less than x squared is greater than -1, multiplying everything by -1, okay? And where does this happen? Well, this turns into a nonlinear inequality that we have to think about, okay? It just turns out that in this case, what? We're really ending up solving 1 is greater than x squared, okay? So x squared has, basically x squared equals 1 at plus or minus 1, and you could make a little table to figure out, okay, -1, 1. These are the areas where x squared is less than 1, and out here is where it's greater. So basically, still ends up being -1 up to 1. The key thing is this substitution. I know the interval of convergence for this u. I have to substitute my value in here and then think about what that means in terms of x, okay? So that's a little bit about using what we know about geometric series to help us a little bit along the way with power series. And that little shortcut can be helpful in some problems in the future. All right, one last little piece here to this section to talk about is this one. Differentiating and integrating power series. So one of the nice things about power series is if you have a nice power series that converges on an interval with radius r, where r is either a positive number or infinity, okay? Then your function is definitely differentiable. And the way you take its derivative is simply by term differentiation, okay? So what that means is what? Well, the k popped out as a multiplier, and then you subtracted k times the derivative of the inside piece, but by design, that's just going to be 1, okay? Integration also works term by term, which is beautiful. So basically here, you could think of pulling that ck out of the integral, okay? Then making a u equals x minus a substitution, du equals dx. And then you're adding 1 to the power and dividing by the new power. And that's how you get that formula with a plus c at the end. Technically, there would be a plus c for every term, but lumping them all together is plus a constant, okay? And we're not going to prove that, but it really follows because you have absolute convergence on that open interval, okay? So as a quick example of that, and then we'll try to dive into that a little bit further in section, I think 11.4, we'll look at a differential equations example. So differentiate the series term by term to find a power series for f prime and identify the function it represents. Okay. So what's the term by term differentiation here? Okay. So for part A, what does f prime look like? Well, if I just think and start differentiating term by term, well, that's going to be 0 plus 1 plus 2x plus 3x squared plus 4x cubed and so on, right? I just took each of these terms and differentiated. Well, the same would work if I did that, by the way, okay? If I sum this up, k goes from 0 to infinity, and I just differentiate each term, that's k x to the k minus 1, okay? So if I started off by plugging in k equals 0, you get a 0 times x to the -1, which is still just 0. When you plug in k equals 1, you get a 1, x to the 0, that's just 1, and so on, all the way down, okay? Now, what does this series represent? Now, and by the way, I could shift the indices a little bit here. I don't want to get too confusing, but I could shift the indices with a little change of variables. I'm going to say m goes from, let's say, so making, here's the change of variables I want to make. M equals k minus 1, okay? Now, if I do that, because starting at 0 is really the same as starting at 1 this time, okay? Because the initial term being 0 there. So that would then start m at 0 at the bottom, okay? And this turns into what? This would turn into x to the m on top there, and the k equals m plus 1. Okay. So anyways, this is that function that we're talking about. Now, how do I know what this actually represents? Well, I can use what I started with to help me understand that, okay? So what is f prime? Well, f prime of x is equal to, it's going to be, I'm going d dx of 1 minus x to the negative 1 power, right? So it's going to be minus 1 times 1 minus x to the minus 2 times the derivative of the inside piece, which is another negative 1 factor, okay? So it's 1 over 1 minus x quantity squared, all right? So it turns out that what we just did was we figured out a power series expansion for this, 1 over 1 minus x quantity squared, without having to use anything special and new, okay? And the same would go for integration. We could integrate term by term, and the integral would be whatever the integral of this function is, which is going to end up being a natural log function, okay? Now, in the interest of time, I'm not going to complete that piece for part B, but it's pretty simple. You actually are just going to, well, we'll write it down. It's okay. I have time. So let's look at B. So what is the integral of f of x dx? Okay, so that's going to be the sum. K goes from 0 to infinity of the integral of the xk's, x to the kth powers. You just integrate term by term, all right? So you're adding 1 to the power and you're dividing by the new power every step of the way. So it's going to be a sum. K goes from 0 to infinity of x to the k plus 1 divided by k plus 1. And then we can tack on one big plus c after the sum, okay? And I could just leave it like this. Again, I could re-index, and re-indexing is kind of, it might look a little bit weird right now, but I'll tell you what, it ends up being a useful technique in the future. So I'll show you again. If I did m equals k plus 1, how would this work? Okay, that would turn into x to the m here. There's an m on the bottom. When k equals 0, what's m? Well, m would be 1, okay? So this would then be the sum. M goes from 1 to infinity, because as k goes to infinity, so does m, okay? X to the m divided by m, all right? Now, what does this end up being a power series for? Well, it ends up being a power series for the integral of 1 over 1 minus x. Okay, well, what the heck is that? Well, let's see. Just making a quick substitution, u equals 1 minus x du equals minus dx, okay? And so this ends up being minus integral 1 over u du, okay? So what is this thing? I guess this ends up being what? Natural log absolute value of u with a minus sign up front plus c, okay? And what I can do is I can at least bring the minus sign up in here. And so this ends up looking like natural log, this is u to the minus 1 power, so 1 over 1 minus x in absolute values plus c, all right? And now what is our, basically, I can probably do a little bit better than this, right? So because x was between negative 1 and 1, what does that mean for 1 minus x? Well, 1 minus x would be, I guess 1 is greater than minus x is greater than negative 1. So adding 1 to each side is 2 is less than x is greater than 0, okay? So this is going to basically work on that interval here, all right? And on that interval, this ratio is always a positive number. So I can actually just say this is the natural log of 1 over 1 minus x plus c, all right? And so this power series that we have here should be equal to this function right here, the natural log function, okay? And we have its interval of convergence. All right, so let's see. Actually, I made one tiny mistake here. That should be 1 minus x. So what I was doing here is I was just making sure that when I did 1 minus x, I have a positive number, okay? I should make the point that the interval of convergence is actually the same initial interval of convergence for the starting function. Okay. So the interval of convergence here was -1 to 1. That means that the interval of convergence here should also be -1 to 1. And I'm going to point out that that does coincide with part of the domain of this natural log function. Okay. Not the entire domain, but part of the domain for this natural log function. A similar thing holds for part A, by the way. Okay. This may be the power series expansion for this particular function expanded about 0. However, they only agree on the interval from -1 to 1. Okay. So one of the limitations that we'll see of power series functions is that they have that kind of nice symmetric interval of convergence. Not every function that we deal with has that same kind of nice symmetric thing. Okay. So in certain ways that can limit their use in problems, or we have to be careful about their use in problems in the future.